So just some announcements. Homework's posted to the 17th, so that's plenty of time. It's 2 multi-part questions, typical for me. The first one you can start now. It's on kind of wave behaviors of particles. It's mostly a plug and chug, a little bit of thinking involved, but not too much math. Just really, the only math is plug and chug. It's mostly just thinking. And then the second part, the second question is, we're not quite ready to tackle it yet, but we should either at the end of this lecture on Monday. Okay, so plenty of time to absorb the material and plenty of chances to talk to me or Sean about it. So yeah, that's due on the 17th, which is a Friday, which is typical. I probably will post the second homework before this due date, but it'll have a long due date as well. So we're still on track for 5 problem sets this semester. Another announcement I wanted to make, this is slowly coming together, but it's more or less confirmed. Again, there's a local chapter of the American Chemical Society, which services us, Yale, Quinnipiac, Southern, Connecticut College, New London, University of Bridgeport, occasionally Wesleyan, Middletown, a number of the schools in the area. They have a student research symposium every year. I think it's every year. But this year it's our year to host it. So it's going to be here at the Bergami Center on Saturday, April 22nd. It'll be posters and talks. So if you're interested in giving a poster on your research or a talk on your research and you just want something on your CV, kind of low stakes, nice inclusive atmosphere, this is a really good place to do it. It's free. Registration hasn't opened yet, but I'll let you know if you're interested. You'll hear from me or someone in the department about it. So it's free. It's on Saturdays, just one day. They'll feed you. For those who are interested in working in industry, there's going to be some people from a number of different businesses holding mock interviews. So if you're interested in trying your interview skills out, there will be a place to do that. Bring your resume and they'll talk to you about it. So that'll be a nice opportunity if you're interested, or if you just want to sit and talk about science and present your poster, that's good too. I'll be there. I'm going to be a judge and doing whatever else I need to do. So that'll be fun if you're interested. Okay, that's all I have to say about announcements. I want to start back up where we left off. We kind of left off in a hurry because I wasn't really paying attention to the clock. So I kind of want to go back and kind of recap the last 30 minutes or so of our discussion. And what we were talking about was the particle in a box problem. And of course, we love boxes in this class. Right, this is the same kind of question that we asked at the beginning of last semester, where we asked about an ideal gas in a box, but now here we've just taken one particle and put it in a box. Right, just a single electron. It can be any particle you want, but electron's always a good example, and you'll understand why we use the electron, why it's an applicable particle to pick in this model very shortly. So the way that it works is we're going to have just find an x-axis, just the distance. We'll plot energy versus it right here. And our box is just a box of infinite walls. So instead of thinking of it in terms of height, think of it in terms of the amount of energy to get to that height, if you will. If you think about gravity being a force, for instance. Right, so energy and height are proportional to each other. And the idea is that we'll start the box at x equals 0. It goes up to infinity. And then the box has length L. And you have a wall that goes up to infinity there. Okay, and what we showed, so let me put my electron in the middle. All right, we're curious about the wave function. Right? The goal we want to find is to find the wave function of this electron in the box. And the way we did that was to come up, define what's called a Hamiltonian, which is the total energy operator. Right, which is going to be our tool for solving any problem. We're going to come up with a Hamiltonian to define our system, and then use our eigenvalue equation, our operator equation from quantum mechanics, the postulates, to solve for the wave function. And of course, the Hamiltonian, which is, I always mark H, it's named after Hamilton, the guy who invented the Hamiltonian, the namesake. He's kind of like the next generation after Newton. Right? So Newton defined Newton's laws, and then they were standardized and generalized by 2 physicists. One was a British one named Hamilton, and the other one's a French one named Lagrange. They have two different approaches to Newton's equations, and we typically use the Hamilton one. You can use either, but it turns out the Hamiltonian is a reasonable, it's just a useful thing for us to use in quantum mechanics. You can use either approach. And we said that it was the sum of the kinetic energy and the potential energy. And then we talked about the kinetic energy. Right, we showed that the kinetic energy is minus h bar squared over 2 times the mass of the electron times the second derivative with respect to position. Right, and I showed that this was equal to the momentum squared divided by 2 times the mass. Right, so that's our kinetic energy operator, and the potential energy was easy because outside of the box the potential energy is infinite, right? It takes infinite energy for the electron to be outside the box because there's infinite walls. And it's free to do whatever it wants inside the box. Right, so it only exists in the box, and the potential is 0 there. The electron the box doesn't influence the electron at all when it's inside. It's just a free box. The electron can freely move around there, just can't escape the walls. The potential is 0. So that means that inside the box, the Hamiltonian is just the kinetic energy, and outside the box, the Hamiltonian is not defined because it's infinite. Right? So we don't worry about outside the box. Right? We know that what this implies is that outside the box, the wave function at any position outside the box is 0. Right? It's not defined. Right? Because the particle's not there. It's never going to be outside the box. So the wave function is 0 everywhere outside the box. So we can just ignore that. Right, we can just analyze the problem inside of the box, and all we have to do is deal with is kinetic energy. And so we went through this process, and what we saw then, therefore, was, right, we're going to use the Schrodinger equation, which says that if you apply the Hamiltonian to a wave function, right, we take the second derivative of it times this constant, we get back a number, which is the energy. Right, this is the number, and we get the wave function back. Okay, so that's the Schrodinger equation. That's how we solve everything. All right, we're going to define a Hamiltonian. And we have an algebraic equation. We have a number, an operator that we define. We can solve for the wave function. And what we showed was that this gets transformed. Let me make sure I have the math proper so I don't screw it up. Actually have fairly detailed notes this time on this problem. We showed that this is equivalent to saying that the second derivative of the wave function with respect to position is equal to a number, which is 2 times the mass of the electron times the energy divided by h bar squared times the wave function. So this is the same. This is equivalent as this, right? Once we do the algebraic manipulations of this operator, we end up finding that the wave function satisfies the property that when you take its second derivative, you get the function back times the number. Okay. And we showed that the solution, I showed that the real solution to this, or a good choice, is a combination of sines and cosines. Right? We showed that this satisfies all the properties we want. We can normalize it by taking the square and integrating and getting a number. It's not unbound. And it satisfies the equation. And we get these unknown constants, a and b. We haven't determined them just yet. But we have this interior, this k, this frequency or wavelength term, which is the square root of 2 times the mass of the electron times energy over h bar. Okay. So the electron acts like a wave, right? It's a sine and a cosine. Let's just ignore one. Let's just say it's a sine for now, okay, just to make it easier. Right? That means that the wave function, so here's my box. The wave function looks like this, like a sine wave. And the number of periods, and how fast the frequency of this wave, or the wavelength, is proportional to this value. to the square root of energy divided by h bar. Right? So this is kind of the frequency of the wave. So as the energy of your electron gets higher, it oscillates more frequently inside the box, right? Just like a wave. Right? This is already completely new physics, because if you remember back when we talked about black bodies like a million years ago at this point, we talked about the photoelectric effect. We talked about how people used to think about waves of light, electromagnetic waves, that the energy that a wave inputs into a system is due to its amplitude, right? How tall peak to peak it is. Right? You can think about that in terms of like water waves, right? The thing that defines how powerful a water wave is not its frequency, but rather its amplitude, right? We think about very powerful waves being very tall, right? And so typically in classical physics, the energy content in a wave is provided by the amplitude. But in quantum mechanics, the amplitude has nothing to do with the energy. The frequency of the wave, how many periods it goes through, is the energy content. Right? And we saw that this is what Planck's law told us, right? Planck's law, the really simple equation, just to remind you, is that the energy of a quantum mechanical system is equal to h bar times its frequency. Right? Energy is frequency. Right? It's totally different than classical physics. Even though we can think of this as a wave, just like a normal, like a wave, the energy content and the physics of it are very different than a classical wave, right? Because the energy is discretized inside of the frequency of the wave itself. It's dependent on the frequency. All right? And that's a very unique concept, right? That's not what classical mechanics predicts. All right, so this is kind of a crazy idea. But we'll see that that actually works out beautifully. Like this is exactly what happens when you put an electron inside of a box. Okay, and so, but we haven't quite figured out exactly what this looks like. Right? We have some unknown numbers. So I kind of started this at the end of class. I just want to go through it again. So let's just come back to our box here. We know that the wave function is a sine and a cosine, so I'll rewrite it here. And what we need to do to determine A and B is to think about what the wave function looks like at the boundaries. Right? We have two fixed points in our system, right? X at the ends of the box. Right? These points never change, right? And the wave function should have a specific value at those points. The fact of the matter is that outside of the box, the wave function is 0. Right? The electron never exists outside the box. So that must mean that the wave function must go to 0 at the edges. Right? So we know that at the edges, we don't know what the function looks like. We know it's sines and cosines, but we know at the edge it goes to 0. Right? So it should look like something like that. Okay. We don't know. But we know that psi of 0 should be 0, right? Because the particle doesn't exist on the wall, right? And as well as psi of L, right? These are both 0. Also, there's one more characteristic, and this helps us confirm that this is a reasonable function to choose, because there are many functions we can choose that satisfy this property, that they go to 0 at the walls. But the function must be smooth and continuous. So, smooth and continuous. What smooth means is that its derivative exists, and continuous means that it doesn't, have gaps. Right? It's defined at every point. Smooth means that d psi dx exists. That's what smooth means for a mathematician. The derivative always exists, and it's continuous, meaning there's a point for every position. And of course the sine, sorry, this should be cosine, I apologize. Of course sines and cosines are continuous, and their derivatives exist everywhere. Right? The derivative of sine is cosine, and the derivative of cosine is negative sine. Those are continuous functions that are defined everywhere, and they're smooth. Okay, so that helps us a little bit. The reason why we have to make this statement is because we could maybe come up with a function that goes to 0, but maybe it looks like this. It's just a hard drop, right? Like a square function. right? But the derivative doesn't exist here, right? It does not exist there. So at that point, d psi dx does not exist, right? So it can't be a hard drop, right? It has to be smooth. It has to be smoothly decreasing towards 0. All right, that really limits the kinds of functions we can have, but it also confirms that sines and cosines are reasonable to represent our electron. Okay, but now we have to figure out the a's and the b's. Okay, so if we have psi of 0 equals 0, then that is a sine of 0 plus b cosine of 0. I think we went through this. And what's the sine of 0? And what's the cosine of 0? 1. And this is 0, right? So this goes away. Right, so that means that b cosine 0, or b cosine 0 is 0, which is only true when b is equal to 0, right? So for the way that we set up the problem, we don't even have to worry about the cosine because b is 0. Okay, so that must mean then that the wave function looks like a sine kx. Okay, we get rid of the cosine part. Now, if we change the way that we define our system and define our box, the cosine might come back, but we just need something that fits our model. We can always change things if we need to. If cosines are more useful. Okay, so now we got to figure out what A is. And the thing is that, remember that on the other edge, psi of L is 0. And the only time that sine is 0, so sine of KL is equal to 0 when KL is equal to 0, which means L is 0. That means we have no box. That's not very helpful. Or where KL is equal to some integer number of pi, right? So it's either at 0 or 180 degrees, 360 degrees, 540 degrees, 720 degrees, right? That's 1 pi, 2 pi, 3 pi, 4 pi. So n is equal to 1, 2, 3, and so on. Okay, so we only have one solution. And the solution is where the interior, the length times this frequency factor k, which is proportional to energy, is equal to some integer multiple of pi. Okay? So it has to be that. But notice that means then that k is also equal to n pi over L. But we have a formula for k. Right? K is equal to the square root of 2 times the mass times the energy of the system divided by h bar. And that's equal to n pi over L. Okay? So this wave function is only properly defined when this is satisfied. But notice, this is very interesting. This means that the energy is proportional to an integer. Right? This n can't be anything except for, right? It's nothing in between. It's 1, 2, 3, blah, blah, blah. Right? So the energy has discrete steps, right? They're integer multiples of itself, which is very interesting. Right? That means the energy can't take any value at once. It only takes specific values that are indexed by n. And in fact, when you do the algebra, just multiply things, square things, and rearrange, we can write the energy as an indexed by this number n, as h squared n squared over 8 times the mass of the electron times L squared. Okay, I think this was kind of where we left off last class. But look, remember when we talked about blackbody radiation, we talked about how the way that Planck solved the ultraviolet catastrophe was to think that the things that emit radiation, the things that emit energy in a black body, emit in discrete quantities, right? They take a frequency of, they take n numbers of a specific frequency, right? You only emit integer numbers of photons, right? And they're discretized by an integer, right? Or the number of quanta, as Planck called it. And here, just by doing this mathematical analysis about the sine wave in the box, we get that discretization immediately. right? That the energy of this electron can only take specific values that are indexed by this number n. Right? If we look at these integers, if we look at the rest of the constants, let's do some analysis and make sure our units are right. So we have h squared over 8 MEL squared times n squared, if you will. Right? So this is just a number. This is joules per second squared over 8 times kilograms times meters squared. And when you do this math out, you just get joules. The second, a kilogram meter squared, those are all units of joules. You get a joule squared divided by joules, and you're left with joules. Right, so what this says is that the electron in a box has discrete energies that are quadratic multiples of a fundamental energy h squared over 8 MEL squared, right? So the energy levels that the system can take are dependent on the size of the mass of the system and the length of the box. Okay? And the spacing between those energy levels depends on the length of the box, right? So as we make the box bigger, the spacings get smaller. All right? I'll show you that. We'll draw it out and it'll all make sense. But first we need to figure out what A is. We haven't quite figured that out yet. Okay? But this is just an aside, right? Just by doing this analysis about the wave function, we've already come up with the energies. Right? This is exactly what we want from the Schrodinger equation, right? We want to solve for the wave function, which gives us the energies of the wave functions of the electron. And the electron, and this idea that the energy levels are discrete, that the electron can't take any energy at once, it has to take specific ones, just falls out of the math. Just falls out of the math. So let's go back and let's define our wave function here. All right, we got to finish it. Okay, so what we're going to do, right? So we already know our wave function looks like this, but we need to solve for A. The way we're going to do it is by using another property that we talked about the wave function. The wave function has one key property. Is that when you integrate the square of it over all space, which is our box, okay, when you integrate over the box of the square of the wave function, you get 1 back. Right? This means that, remember what this means, I'll drive this point home time and time again, that what this means is that the probability of finding the electron in the box, anywhere in the box, is 1, right? 100% chance. Right? That's exactly what this is exactly what this is saying, right? That the wave function encodes the probability about a particle, about the electron being in a certain position. That's what psi squared tells us. And when you integrate over the entire probability distribution, or the entire space, it should be 100% there should be a 100% chance of finding the electron. So it integrates to 1. Well, that gives us a way to, if we integrate this over the box and set it equal to 1, we can solve for A. Right? That's the only thing we don't know. So let's do that. So we have 1 equals the integral of the square of this. So that's A squared sine squared kx dx. Right? A is just a number, so we can bring it out. And we want to we need to do the bounds of the integration too. We have to integrate over a space. And of course the space where the wave function is defined is the box, just the box. So we integrate from 0 to L, sine squared kx dx. Let me let's replace k. Remember that, just to remind you, I deleted this, but remember that k is equal to n pi over L. That was what we determined. That was the bounds. That's what allows the wave function to go to 0 at the edges. So this is 1 equals a squared integral from 0 to L of sine squared n pi over Lx dx. Okay. So now we just have to integrate a sine squared. That's a one that you can do. I'll show you, actually, I have a really nice resource on Canvas for these kinds of integrals. We're going to see integrals of sine squareds and sines and cosines all the time in this class. So I won't really go through the way to solve it. You can just solve it with Wolfram alpha, or you can look it up in a table. I have a list of tables of integrals for this class on Canvas. I'll show it to you at some point. But I'll kind of give you a sense of how to solve this problem. Maybe you haven't done this in a million years. So we'll do what's called a U substitution. Right, and what we'll do is we'll let U equal n pi over Lx, which means that du is n pi over L dx, which means that dx is equal to L over n pi du. Okay, so let's rewrite this integral with the U substitution. We have a squared. We have to figure out the bounds of integration. We'll do that in a second. We have sine squared u. And then we got to replace dx with L over n pi du. So that's 1 equals a squared times L over n pi times the integral of sine squared u du. All right, and then we got to figure out where we integrate from. Now we have to transform the bounds of this integration as well, because dx is being transformed into du. And what it turns out to is that you're integrating from 0 to n pi here. So now we have an integral of sine squared. So I'll just give you the result. So the L over, that's the factor on the outside of the integral that we get. And then the integral turns out to be n pi over 2. So we're left with, and this is equal to 1. Right? It's all equal to 1. Right? So now we can solve for a. Right? A is a function of pi. N, well, it's not a function of n. The n's cancel, right? The n's pi cancel out. So a squared L over 2 is equal to 1, which means that a is equal to the square root of 2 over L. Okay? So this is the constant on the outside that allows us to ensure that when we integrate the wave function across the entire box, we get a 1 out. Right? This is what we call a normalization constant. Right? And that's just to confirm. Notice that if I don't have a normalization constant and I integrate, I don't get 1 out, but I get L over 2, right? So in order to make sure that I integrate and get 1, then I have to multiply it by the square of 2 over L. Right? And then it cancels out and you get 1. So that's what we call a normalization constant. And this is the kind of routine that we're going to do. We're going to define a Hamiltonian, come up with an algebraic or a differential equation that allows us to solve for the wave function. We're going to make sure that the wave function works, it satisfies all the properties, and then we normalize it so that when we integrate the square, we get 1 back. Okay. We have everything we need, right? We've now determined everything about our wave function. So the wave function for this system, again, it's a function of n. Right? There's an n inside of the wave function, right? It's each there's n wave functions, and each of them have a different property, or different wave, or there's different levels, right? They have different energies, and each one has a different wave function. And that's 2 over L times the sine of n pi over L times x. Right? We now have a full wave function that allows us to calculate anything we want about this electron. Right? That was the whole point, is that the wave function completely defines the electron in this box, right? And now we know exactly what that electron looks like mathematically for any energy. Remember, each of these wave functions are associated with a specific energy, which is h squared n squared over 8ml squared. Okay, so your box, your electron has discrete energy levels. N equals 1, n equals 2. Remember that n is greater than or equal to 1. There's n equals 1, n equals 2, n equals 3, n equals 4. They have different energies that are spaced individually, and each one is associated with a specific wave function. So basically, the behavior of the electron changes depending on its energy. Right? So for each energy level, there's a specific wave function describing the electron in that energy level, and they look like different signs. Right? So each one you go up, the sign gets its sign of pi over Lx, and 2 pi over Lx, and 3 pi over Lx, and so on and so forth. Right? So each energy level the electron can be in has a different wave function. Let's plot them. What you get are really beautiful pictures. What I'm going to do is I'm going to draw 2 more boxes. Let's make them bigger. Sorry. Let's make them nice and big on the board. Right, I'm going to draw 2 boxes because I'm going to plot 2 different things. What I'm going to do is I'm going to plot on this one this the wave function, and over here I'm going to plot the square of the wave function. Right? That's the probability. Right? And we know that they only, and that the y-axis here is energy. Just as a reminder, this is energy. You can think of this as 0 to L on the x-axis. Right? It's the same plot as before. All right, let me make sure I have my notes right for this. Oh, they're over there. Right. Okay, so again, there are discrete energy levels, so the system can only exist at very specific energies. So let's write n equals 1 here. Okay, and I'll put the energies. Let me put it on the right side, and I'll put the energies on the left side. So the energy of this is going to be h squared over 8 mel squared equals 1. And the wave function, let's just write it down, looks like the square root of 2 over L sine pi x over L. Right, n's 1. And when you plot this from 0 to L, what you find is that it's a wave, it's a sine wave that's completed in 1/2 period. Like that. And then, of course, if you square that, it looks almost exactly the same. Something like that. Pretty similar. Sine, if you square a sine like that, and sine squared, they look basically the same. What does this tell us? Well, first of all, it tells us that the electron, the first important thing is that the electron, there is no n equals 0 level. Right? If we set n to be 0, which would mean it has 0 energy, right? Which is nice. We want a ground state, right? We want to. What's the lowest energy the electron could be at? We would think, okay, n equals 0. Energy is 0, but the wave function is 0, right? Because it's sine of 0 times x, which is 0. So the wave function is undefined at n equals 0. So psi squared is 0, which means there's no probability of ever seeing a particle in an n equals 0 state. It doesn't exist. So an electron inside of a box always has energy. It always has this much energy. You can't have any less. If it had any less, it would be n equals 0, and then it doesn't exist anymore. Right? So no matter how, imagine that this is a box, you could cool it down to the lowest temperature to cool that electron down as much as possible, pull the energy out of it. No matter what you do, it's always going to have this much energy. Well, that's strange, because that doesn't make any sense. Why the hell does it, how can a particle always have energy? Right? How can you not pull out this fundamental part of the energy? Right? It's always this. This is the lowest energy you can have. That's greater than 0. And the fact of the matter is that's just what quantum mechanics is. That we're going to find this time and time again. That systems, certain particles, certain systems, like a particle in a box, or we'll talk about bonds. Bonds have this example, is that no matter when you get to the lowest energy level, right, the lowest energy the system could possibly have, the energy is not equal to 0. Right? So no matter if this was at 0, right, if you cool this down to a nanokelvin, right, a millionth of a degree of Celsius, right, as cold as you can possibly get it, you will always read out that the electron in that box is moving around with this energy. You can't get rid of it. This leftover energy we call 0 point energy. All right, we're going to find many systems in this class, the bond being the most important one, that exhibit this 0 point energy. The fact that a system like this can't have 0 energy. It's impossible. 0 energy for an electron in a box means there's no electron. It's the only way you can describe that. So quantum mechanical systems always have this little residual energy that you can't get rid of, the 0 point energy. Right? This has extremely important consequences. I think it's better to see those consequences in the context of a bond, so we'll come back to it later. This has very big consequences, and it's a consequence of a very important point about quantum mechanics that we'll talk about called the Heisenberg uncertainty principle. Right? We haven't quite gotten there yet. But this is intrinsic to a quantum mechanical system. It's intrinsic. It's something unique that classical physics can't reproduce. In classical physics, you can take an electron and cool it down all the way you want, 0 energy, which means it's standing still. Right? That's the important thing. So there's no energy, it means it's stationary. What this is saying is that an electron can't be stationary. It always has to be moving, no matter what you do. Even still, so accepting that, we take that limitation and we move on with it. We still don't even know where the electron is. Right? Remember that this is equal or proportional to the probability of finding an electron at a point in space. Okay? So, for instance, let me draw this with some other colors. Green. If we want to say focus in, we take our electron microscope and we focus into a particular region. We're saying, is our electron in this region? We'll call that x plus dx, right? We're going to look in this small region with our camera and ask the question, is the electron there or not in our box? And the probability of observing in that region between x and x plus dx is the integral from x to x plus dx of psi squared dx. All right, and that's less than 1, right, by definition. Right? We only get probability of 1 when we look at, if we ask the question, is it in the box at all? So that must mean that the probability of finding it in a small part of the box has to be less than 1. So that means that even though the electron's in here, you don't actually know where it is. It's random. It's a probability distribution. So every time you look in this region, you take a picture of that region, there's only going to be a finite probability you're going to see the electron there. Right? In fact, what we interpret is that the electron exists in all of this space, and when we make a measurement of its position, we're going to get a random result out, and the probability of getting that random result is psi squared. Okay? So notice that what that means is that in the box, there's low probability to find it near the edges because psi squared is small, and there's a higher probability in the center. So even though we might know that the electron's in the box, we don't actually know where it is. In fact, its position is random, and we can only calculate the probability of seeing it in a certain region. Okay. What we call that, right? So what that means is that the position of the electron is not localized, right? It's not like the electron position is just a little impulse, right? Like this. Right? The electron is precisely there. Right? It's not like that. The electron's position is distributed across the entire box, and all we can say is we kind of know where the probability of it is, and on average it's kind of in the middle, right, where the probability is highest. Right? That's all we can say about this electron. Right? So we often say that the electron is delocalized in the box. Right? Maybe you remember delocalization when we talk about aromatic systems like benzene, where the electrons are delocalized in the ring, right? We're going to see this electron, this box system. This is going to come in a huge handy when we talk about things like benzene, right? Where we talk about delocalization, where electrons are shared amongst multiple atoms, right? This is the exact same idea, right? Here you just have a box. Imagine that this is a bond between two atoms. You have an atom here and an atom here. And what it's telling us is that an electron exists somewhere in the middle, and it's just kind of shared from one end to the other, right? And there's a probability where it's going to be, and on average, it's going to be in the middle. All right? That's all we can say about it. Right? We can't localize it any more than that. Now, so we'll have to think about that a little bit when we want to calculate what's the average position of our atom or our electron. What's the average, right? That's all we can ask. What's the average? Right? That's all we can do. We can ask for an average position. It's the best we can do. Okay, and we'll talk about how to calculate average values at the end very soon, next 20 minutes or so. Okay, so let's keep going up, right? I've only talked about n equals 1 here. So let's go up in energy level. Of course, there are infinite energy levels. Remember, the walls are infinitely high. So the energy for this electron can be infinite, right? It has infinite levels. So let's go to the next one. N equals 2. The energy of that one is going to be n squared. So the energy of this one is 4h squared over 8mel squared. So it's 4 times the energy. And I'll just write n equals 3 because we'll draw it as well. That's 9h squared over 8mel squared. Okay, what do these wave functions look like? Well, remember n equals 2 is going to be the square root of 2 over L sine 2 pi x over L. That means is that it has twice the frequency. The wavelength is half, if you will. And so that means it completes one whole period in the box. So the wave function looks like that for n equals 2. And what does the square look like? Well, it kind of looks like this. This is a poor drawing. Let me make that so it's not a cusp. My apologies. Well, that's good enough. All right, so it looks like that. And I'm just going to go ahead and draw n equals 3. It makes 1.5 periods. So it looks like this. And if we draw the square of it, again, it looks like this, like that. Okay. What does this tell us? Well, again, the energy is increasing. But notice that something's happening to the wave function in the middle of the box now. N equals 2. Right? It changes, the wave function changes sign. Right? It goes from positive to negative at n equals 2. So when we take the square of it, which is what we actually observe, the probability, right, the probability distribution of its position, there's a region where the probability is 0 in the middle of the box. Right? So at n equals 1, if we look at the psi squared, we expect the electron to be in the middle on average, right? Because the probability is highest in the middle. But then when we go to n equals 2, there's a 0 point there, right? It goes to 0. There's no probability of seeing the electron there. Psi squared is 0 at that. Right? We call these nodes. Okay, and that's a really unique part about quantum mechanics. Because if this were classical, if this were a particle in a box, like we did in thermodynamics, just a normal particle moving around randomly with Newton's equations, we would expect that there's a probability, no matter what the energy is, there's a probability of finding the particle in the middle of the box no matter what. Right? The particle can exhibit any position at once, classically. Right? It could be here, it could be here, it could be here, it doesn't matter. It doesn't care. But quantum mechanically, because of this wave-like property, the wave property, you end up getting these whole periods of your wave where the wave function crosses 0, which means when you square it, the square is 0. So there are regions quantum mechanically that the electron can't exist in. We're going to see this over and over and over and over again, right? Because everything's going to have this wave-like property, right? Everything's going to look like a wave. There's going to be signs, it's going to be oscillating. be some oscillations, and there's going to be regions where that wave function crosses 0, which means that the probability of finding that crossing point is 0, just like this. Right? And so even the electrons not only don't move and exhibit energy like a classical particle, they can't even exist in spaces where you would expect classical particles to be, right? Because of this wave property. Notice that as we go up in energy, the number of nodes increases. Right, if you go to n equals 4, notice that we have 0 nodes, 1 node, 2 nodes. You go to n equals 4, you have 3 nodes. Go to n equals 5, you have 4 nodes. Right, so there's always n minus 1 nodes. All right, and that's the fact that notice that every wave function is either a half wavelength or a whole wavelength of a wave. Right, this is a half wavelength. This is a whole wavelength. This is 1.5 wavelengths, and the next one's 2 wavelengths, right? 2 periods of the wave, and so on. Because of that, it's going to cross 0, and it crosses 0 n minus 1 times. So as you get to higher and higher energy, the region at which the electron can exist gets narrower and narrower. Right? For instance, imagine that you're at, so I'm just going to take our box and extend it up really high, go to n equals 100. Right? What does that look like? Well, I can't draw it, but it's going to look like, the wave function is going to look like this. Like that, right? And so the psi squared, what does that look like? Well, it looks like, well, let me draw so it doesn't go to 0, but it looks like a comb. Right? There's going to be 99 nodes and 100 different places they can exist in. Let's go to n equals 1,000. Right? The wave function oscillates so fast that you can't tell it apart. But when you square it, it's mostly above 0. It's just down for just a second. Kind of looks like that. But there's this little tiny combs. The combs get smaller and thinner as n goes to infinity. But eventually, once you get to n equals 1,000, it's going so fast that when you square it, it basically looks like a square. Right? The place the nodes where it goes to 0 are so tiny in width that you can't really tell it apart at this scale. So notice though that this is exactly what we would expect for an electron that works classically. Notice that the nodes, the places where it can't exist, are so small and so numerous that at the scale that I'm drawing this, you can't even see them. Of course, that's not really what this looks like, but right, there's this tiny little nodes. They barely take up any width of the function, and so on and so forth. And so what that would imply that when I zoom out and I kind of blur my eyes, that the psi squared for this super high energy electron looks like it can exist anywhere in the box. Right? There's an equal probability of existing anywhere. Right? That's just classical behavior. As n approaches infinity, psi squared becomes kind of a square, right? A constant probability, right? And this is what you would expect classically, right? That the electron has an equal probability, right? There's no potential here, right? So classically, there's no reason there's no impetus for the electron energetically to be in the middle than it is outside. So classically, you would expect that the probability distribution is flat. There's an equal chance of seeing the particle, the electron, anywhere in the box. Right? But that we only see that behavior when n is very large, when the energy level, when the energy electron is massive, which is what you would consider macroscopic energies. Right? So the idea is that classical mechanics emerges from quantum mechanics. Right? So when the system is so low in energy, that you're in this kind of microscopic scale of energy, right, an atomic level of energy. You have these discrete levels where there are very non-classical behavior, very wave-like behavior. And the moment you kick the energy up of this wave so much, the wave stops acting like a wave. It starts acting like a particle, like a classical particle, and it can exist anywhere in the box. Right? That's classical behavior. Right? And you'll see this time and time again, this smooth divergence. You'll go from pure quantum mechanical behavior, and as energy increases or the size of the box increases as well, they're turned out to be equivalent comments, the behavior of the electron becomes less and less wave-like and more particle-like. Right? And so once you get the electron, you pump it up high enough in energy that has a macroscopic amount of energy, number of joules or something like that, something that you can measure macroscopically, it acts just like a particle, right? That it can exist anywhere in the box, it just moves around, it doesn't matter. Okay, so this is what's called the correspondence principle, the idea that classical mechanics isn't orthogonal or separate from quantum mechanics, but it appears naturally out of quantum mechanics when you leave the microscopic regime. Right? By microscopic, I mean small length scales or large energies. Microscopic, small energies or small length scales. Okay, so this is small energy, small length scale, we get wave-like properties. Large energy, large wavelength scales, we get particle-like properties, classical properties. Okay, so we're going to see these energy level structures over and over and over again, right? It's amazing that every single particle, you put it in every single system microscopically, when you put it in a system that's physical, it's well defined, you get this level structure, these quantized energy levels, where the particle can exist in between them in energy, and they have these weird wave-like properties, these wave functions. Okay? This is every property, you're going to see this time and time again. Okay, so anyway, so this is kind of a general overview of wave functions. Right? There's this wave-like property that gives you emergent particle-like property when you jank the energy up really high. But now I want to ask a different question. The question is, how do we ask this thing questions? Right? We've gotten the energy. Right? We know the energy of the system, but what if we want to ask the particle what its momentum is, the electron? What's its average momentum? What's its average position? Right? Or maybe there's other properties we want to ask it. So we have to come up with a way to ask a wave function a question. Right? Unfortunately, the wave function can't give us a definite answer, right? Because a wave function is, in terms of probability, delocalized. Right? All it tells us is the probability. It doesn't tell us exactly where the particle is at all times. It just gives us a sense of where it is on average. So we have to ask it a statistical question instead. Right? We have to ask it, instead of asking what is your position, we ask, what is your average position? Right? We're going to ask about averages, because that's all we can ask it, right? All the electron gives us is a probability distribution, something that we can average over. So the probability of grades, or probability of positions. And so we can only ask it questions about averages. Right? We can't ask it precise questions. We can only ask about statistics. So now the question is, how do you do statistics on a wave function? How do you ask it statistical questions? And there's a really easy formula for it. And this starts our next postulate. So I call this one postulate 4 in my notes. Average observables. Okay? So if a system is in a state represented or described by a normalized wave function, all right, psi, call it psi of n of x, for instance. Then the average value of that physical observable, energy, position, momentum, and so on, is calculated given by the following formula. Okay? So if an operator A applied to the wave function returns a number times a wave function, right? If A is a linear operator, then the average value of the little a, the number, the observable, which we write with angle brackets a, this is the average of that observable, is given by the integral over all space of psi times the operator times psi dx. All right, so what we're going to do is we're going to take psi squared and we're going to jam the operator in the middle. Okay? All right, so every time you need to calculate an average value, basically the idea is that we're going to integrate over the probability multiplied by the variable, the observable itself, right? That'll give us an average. It's an average value, just a normal average value from calculus. Right, so every time, unfortunately, every time we want to calculate a value, an average value, we have to take an integral. But some are easier than others. For instance, let's, for instance, calculate the average value of energy. For our particle in a box. So PIAB particle in a box. So that's going to be the integral from 0 to L, that's all space, of psi of nx times the energy operator, which is h, psi of n of x, dx. All right, we're jamming that operator in the middle of the psi squared. You'll understand once we get through a little bit more math and talk a little bit more about wave functions why we have this structure. We're not quite there yet, though. So just hang on and just use this as a tool. But by the Schrodinger equation, h psi is equal to E psi. Right? When we apply h to a wave function, we get its energy back. We can plug that in. 0 to L psi n of x, and then we can apply this formula, so we get E n psi n of x dx. All right, and E n is just a number, it's just the energy. All right, so we can factor it out. And we're left with 0 to L of psi n of x dx, which is E sub n integral of psi squared dx, which is 1. Okay? So it's not too hard. The average energy of our system is the energy that we get from the Hamiltonian. Right? Exactly what we would expect. Right? And we know what that is. We already wrote it down. It's h squared n squared over 8ml squared. Right? All right, so this math isn't too difficult when you do something that's like this, right? When you have a Schrodinger equation, you know the energy, then all you have to do is just read out the energy and you know the average value for the energy. So that's nice. That means the energy is well defined. Right? The important thing to note is that energy is well defined and has no uncertainty. Just one value. Okay, so that's really nice. Right? At least we know when we measure an energy of an electron, we know we're getting not an average value, we're getting the value. We only take on one value, that's the entire point. Right? So this all makes sense. But now let's think about a different question. Let's think about position. Okay, so what's the average position? Of our electron. 15 minutes. Okay. All right, so the operator for position is x, well, x hat, which is just x. Okay, that's really easy, right? You just take the variable for the position. So that means that the average position of that value of x is x, integral from 0 to L of psi of x hat is psi, and x hat is just x, dx. But now we can't factor anything out. X is a variable, it's not a number. Right? So we have to integrate over it. So I'm going to expand this out. Right? So this is 0 from L of sine n pi x over L, x, sine n pi x over L, dx. Right? That's our wave function. We could pick an x, right? We can pick an n if we want, right? If we want, or we can integrate with generic n as well. But in general, this is going to simplify to 0 to L of x times sine squared n pi x over L. Right? This is why we need to integrate. Because sometimes you're going to ask a question about a variable that's not well defined, or it exhibits a statistical distribution, which means you have to integrate over that variable. Right? So the x ends up being a part of this integral. And so in order to calculate it, we have to calculate sine squared, but we also have to multiply by x. Okay, so this is the average value. All right, so this integral, it turns out to be a little harder to do than sine squared. You have to do integration by parts. But I'm going to, again, I'll show you in a second, or I'll make sure to remind you, I'll send an announcement that there's a beautiful PDF table in Module 0 with integrals, table of integrals that are appropriate for quantum mechanics. And we're going to see the same integrals over and over and over again in this class. So I won't walk through how to solve them. Instead, I'd rather you guys understand how to look up a table and find the result. It's just much easier to do that. These aren't hard integrals to do. They're Calc 2 integrals, but it's just a waste of time in this case, I think. So let's go ahead and calculate this. So let's let n equals 1. All right, so let's ask the question, what's the position, average position of the electron in its ground state? All right, so that integral needs to be 0 to L x sine squared pi x over L dx. All right, so we have to do integration by parts and use substitution. It's a really messy integral. But you can look it up in the table. Oh, we missed, sorry, I missed a, there's also, sorry, there's the normalization constant, square root of 2 over L here. I apologize. That's normalized. So we have a factor of 2 over L squared, square root squared, so this is 2 over L on the outside. Sorry about that. Always forget my normalization constant. But anyway, I can look up this integral. No problem. It's in the book, too. There's a table of integrals in the book. And so you get 2 over L, and the integral itself is L squared over 4. Okay, and so let's do this math. L's cancel out, you're left with L, and the 2's cancel out, so you're left over L over 2. So the average position of the electron in the ground state is halfway through the box. Well, that should make a lot of sense. Let's look at the drawing again. Here's n equals 1. Remember that the wave function is 1/2 wavelength. So it's like that. Well, there's equal probability. Let's subdivide it into half. So here's L over 2. Here's L and 0. Right? There's equal probability of it being on the left side as they're on the right side. Right? The wave function is cut in half. So if there's equal probability of it being here and here, then that means that this is the average. Right? In the middle. Right? So that makes a lot of sense. What it basically means is that the electron is propagating back and forth in this well, if you will, in this box. Remember, it's a wave. It's literally moving like this, and it's equally on the left side in time as it is on the right side. So on average, it's in the middle. Okay. Now we can ask that same question. And let n be any number, right? Does n change? Or does the average value of x change as you go up to higher and higher levels? And that's on the homework, so I won't answer that question for you. The math is very similar. You just have an extra factor of n here you have to deal with. And you'll find that the answer is very rational. Of course it's rational, but in the sense, I mean rational in the sense that it makes sense. That it's not anything crazy if you assume that the electron is a wave. The result is exactly what you would expect. Okay, so that's what this electron is doing. It's bouncing this way, it's bouncing that way, equally amount, and on average, it's in the middle. Okay, so that tells us about the position. All right, so what about its momentum? All right, so position only tells us part of the story. It tells us where it is, but it doesn't tell us how it's moving. Right? The particle has some, imagine the wave has some velocity. The particle has some velocity, right? It's moving this way, it's moving this way. How fast is it moving? Right? What's its momentum? So let's ask that instead. We're going to ask the average value of P. The operator for P, we talked about it last class, is minus IH bar d by dx. So we just take the integral from 0 to L, and put the 2 over L on the outside. And we'll do n equals 1, just to make it easy. Pi x over L, sorry, times minus IH bar d by dx, sine of pi L x dx. Okay, so let's look at how we evaluate this. Notice I can't move this sign over here and immediately make sine squared because this sign is being modified by the operator. Right? The operator is telling me that I need to take the derivative of this first. Right? So the operator is operating on what's in front of it, right? And so I got to take a derivative. Right? So that's going to be equal to 2 over L. 0 to L is the first term, sine pi over Lx. Minus IH bar. We'll just hold on to that for a second. And then we have to take a derivative of the thing inside, right? The derivative of the sine, right? And so, of course, the derivative of the sine is just cosine. We get a factor of pi over L from the chain rule. Cosine pi L x dx. Okay. So we have a bunch of terms to collect. This ends up being 2 minus 2 IH bar over L squared times the pi. There's a factor of pi here as well, 2 pi IH bar over L squared. Right, I'm just bringing all the constant terms out. Times 0 to L of sine pi over Lx times cosine pi over Lx dx. Okay, so now our integral for momentum isn't sine squared, but sine cosine. All right, so I'm not even going to evaluate this integral just yet. Let's just plot this and see if we can figure out what the integral value is, just by looking at it graphically. So I'm going to draw an x from 0 to L here. All right, and let's plot the sine and the cosine. So we know what the sine looks like. It goes, here's the sine. There's the sine. This is sine pi x over L. And cosine at 0, cosine of 0 is 1. Let me draw those like this instead. We'll draw this as 1. So the cosine function starts at 1, and then on the other bound it's going to be a 1 as well. Or no, it's not. It's going to be negative. So it's going to go like this, like that. Is that right? That's right. That's right. So now let's integrate this function. Now notice, I didn't draw it that well. Oh, sorry, it goes to -1. I apologize. It goes to -1 here. So the cosine function over the box goes from 1 to -1, and the sine function goes from 0 to 1. Now the important thing to note is that this area right here, the area under the curve negative, is equal and opposite to this. So the integral of cosine pi x over L from 0 to L is 0. Right? Because you integrate, you add area under the curve, and then you subtract all of it out. Okay? And so when we multiply these two functions together, what do we get? Well, this function is symmetric. The sine function is symmetric about the halfway point of the box, and that's where the cosine function changes sign. So the product of the two 1 minus 1. So the product of the two, let's see, at here it starts at 0, right? Because sine is 0 here and 1, so it's 0 there. It's going to be 0 here in the middle, right? Because cosine 0 here. And it's going to be minus 1. It's going to be 0 on the other side. Right? So there's 3 zeros to this the function. They're both positive here. So this part's positive, and this is negative by the same magnitude. So the product looks like this. Right? So then when we integrate over this, we get some positive value, and we get equal and opposite negative. So the total integral is 0. Okay? So that means when we integrate this function, we don't even have to do the calculus. Right? We just graph it, and we know, okay, the whole thing integrates to 0. Right? So what does that tell us? Well, that tells us that the momentum of our particle in the ground state is 0. What does that mean? Well, that must mean it has no velocity. Right? Remember that P is equal to mv for a particle, but remember we also learned that P is also h over lambda, right? So depends on the way you want to think about it. But what it means is that you're thinking, okay, well, that must mean it doesn't move at all. But remember, velocity is a vector. It has a direction. So in fact, what this means is, so here's our box again. I'm going to draw our wave function. And I'm going to subdivide the box into two parts. What it means is that every time you ask the question to the electron, what's your momentum? Well, it's going to give you a value. Sometimes it's going to be going in this direction. Right? It's going to say, oh, my momentum's positive, I'm going this way, 50% of the time, moving towards the right wall of the box. And then 50% of the time, it's moving to the left side of the box. Okay, so the particle has a momentum, but the fact of the matter is that the momentum is either negative or positive half the time. So P is 0, 50% of less than 0 half the time, and P is greater than 0 half the time. So that means that the average is 0, right? The negative and the positives cancel out. So what that tells us is that the particle is moving in both directions equally likely, right? It's either moving to the left or moving to the right, and so on average it's not moving at all. Now here's a different question, and this is on the homework. What about p squared? Right? When you square a vector, you lose the directionality of it. Right? The v squared is just the length of the vector. Okay, so there's no direction, it's just a magnitude. Right? So the question that you might want to think about is p squared not equal to 0? Is the magnitude of the momentum well defined? Is it 0? Right? So if the idea is that if p average is 0, that means the particle moves left and right equally. But if p squared is 0, not 0, then that means that the particle has a non-zero velocity, or non-zero speed. But if p squared is 0, that means it's not moving at all. Right? So that's something to think about. And the homework asks that question. Right? To calculate p squared instead. Now what you should find, maybe if we think about it a little bit, we mentioned that here's a hint. Remember that we said that the kinetic energy is p squared over 2m. We know the system has kinetic energy, right, because it has an energy level. And we said that all that energy is kinetic, has a fixed energy. So that must mean p squared must not be 0 either. Right? So if there's an average kinetic energy, which is the energy of the system, then that must mean p squared must not be 0 too. So what's happening is that the particle is very much moving. Right? It's propagating through this box, bouncing back and forth, but it doesn't have any preference of going left or going right. So half the time it's propagating in the reverse direction, half the time it's propagating in a forward direction. And on average, that means it's 0. Okay? So what we know is that all we can say about our electron, the most precise thing we can say about our electron right now is that on average it sits in the middle. On average it's either propagating this way or propagating this way, and it's probably doing it at some velocity, right? There's some propagation velocity that's moving back and forth like this. Okay? That's all we can say about it. Right? That's all we're going to be able to observe. On Monday, I'm going to show you, we're going to do some, I'll start some chemical applications of this, and I'll show you some pictures of doing these kinds of particle in a box experiments on molecules. Okay? When you take a photograph of a molecule, all right, we'll look at some photographs of molecules, you're measuring psi squared. All right? If we think about a bond as a way that you contain electrons that they move around, this particle in a box analysis might tell us a lot about what molecules look like when we take pictures of them. Okay, so we'll start that on Monday. And continue on through our journey of our particle. Yeah, you too.